tensors.
Hi, so thanks for having me here. So the first 2/3 of my talk, I'm going to talk about symmetric orthogonally decomposable tensors, which some of you might have heard me talk about before. And then the last third, I'll talk about the non-symmetric case. Okay. So I'll start by reminding people about symmetric tensors. So let T be an n by n by n d times symmetric tensors with elements in some field which in this talk will be either the real numbers or the complex numbers, and it'll be k if it holds for either of them. And then T is symmetric if if T I1, I2 through ID equals T I sigma 1 through I sigma d for any permutations of the indices. Okay, that's what symmetric means, and the simplest example is the case of d equals to 2 symmetric matrices, which we all know. So T is an n by n symmetric matrix. And for example, if n equals 3 and d equals 3, we have an 3 by 3 by 3 symmetric tensor. And since it's symmetric, we might as well, for simplicity, denote each entry T, I, J, K, just so put I, J, and K in increasing order or non-decreasing order. So an equivalent way of thinking about symmetric tensors is by polynomials. So if T is an n by n by n d times symmetric tensor, we can think of it as a homogeneous polynomial in n variables of degree d. So for matrices, the way this works is we just take f of x1 through xn to be x transpose tx. Okay, so T is a matrix. And now this is a homogeneous polynomial of degree 2. And knowing this polynomial tells us exactly what the matrix is, and vice versa. So for a general symmetric tensor, we can look at the polynomial f of x1 through xn equals t times x to the d. That's a notation. So we sum over all of the indices, I1 through id, from 1 to n. And then we take t I1, I2 through id times xi1 times xi2 times xid. And if we want to group all terms that have the same monomial, then so we look at the monomial x1 to the j1 times dot 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 xn to the jn. And since our polynomial is homogeneous of degree d, then the exponents have to sum to d. And then there are this many of them. D choose j1, j through jn, some multinomial coefficient, and then the entry from the tensor. Okay, so since it's symmetric, we can just look at one of them. And knowing this polynomial tells us exactly what the tensor is. We can use different coordinates. For example, so indexed by j1 through jn, the indices of the monomial. Okay, so if we have a 3 by 3 matrix, then the polynomial is a polynomial in 3 variables of degree 2. So equals this sum I1, I2 from 1 to 3, Ti1, I2 times xi1 times xi2, and we can group together the monomials, and then we have this representation. So sometimes it's easier to think about the homogeneous polynomial than the symmetric tensor, because the symmetric tensor has so many entries, but they're all equal, whereas the polynomial is somehow a little bit nicer. So what is symmetric tensor decomposition? You probably all know by now. So decomposition of a tensor is just an expression for the tensor as sum I from 1 to r, lambda I, vi to the tensor power d. So here this is symmetric. And for the corresponding polynomial ft, this is the same as writing it as sum I from 1 to r of lambda I times these linear forms to the power d. So with the same vectors, vi. So we take vi1 x1 plus vi2 x2 plus vin xn to the power d. Okay. And the smallest r for which such a decomposition exists is called the symmetric rank of t. So an orthogonal tensor decomposition is of a symmetric tensor. It's again a symmetric decomposition, but now we also require that the vectors v1 through vr, we require them to lie. So now our tensor is real, and we require that the vectors v1 through vr be real and orthonormal. So in particular, there can be at most r of them, at most n of them, because we have at most n orthonormal vectors in Rn. Okay, and we say that the tensor is orthogonally decomposable, or Odeco, if it possesses an orthogonal decomposition. And so here are some examples. So for matrices, for real symmetric matrices, by the spectral theorem, we know that every real symmetric matrix has an orthonormal basis of eigenvectors, v1 through vn. And we can express the matrix as v transpose times lambda times v, which if you write it as a sum, equals exactly sum I from 1 to n, lambda I, vi to the tensor power 2. So every symmetric matrix, every real symmetric matrix is orthogonally decomposable. So now we're asking what happens if we have a tensor. So which symmetric tensors are orthogonally decomposable? So the simplest example would be the so-called Fermat polynomial. So I take the tensor t, which is e1 to the tensor power d plus e to the tensor power d and so on plus en to the tensor power d, whose corresponding polynomial is just x1 to the d plus x to the d plus xn to the d. So that's is the simplest possible example for general tensors. And that's definitely orthogonally decomposable. So where did I first see this? So I first saw this in a machine learning paper by Anand Kumar and Ronge and Daniel Su and Kade and Telegarsky, some of whom are speaking tomorrow. So this is a statistical model which models documents that have d words, and each document has one topic, okay? And the way we generate such documents is as follows. So we first pick h, which is a topic, and it's so it takes values from 1 to k, and its distribution is given by this vector w. And once we pick a topic, then we pick each of the d words, IID at random, with distribution mu j. If the topic is j, their distribution is given by mu j. So they're independent given the topic. Okay, and we observe documents, and we try to recover the distribution. So we try to recover the hidden parameters. So basically, we're only going to observe the words in the document. And so to see what I mean, the joint distribution of the words x1, x2 through xd can be encoded in an n by n by n d times tensor, which we'll see later as symmetric. So what is this distribution? We have to, so since they're independent given the topic, we sum over all the possible topics, j from 1 to k, the probability that the topic is j, times the distribution of the words given the topic is j. So it's basically equal to, so this p of xi given h equals j is just a vector defining the distribution of the ith word given the topic is j, which, as we said before, is mu j. So the joint distribution of these variables equals exactly sum j from 1 to k, wj times mu j to the tensor power d. So this is exactly a decomposition of this tensor in, with rank at most k, I guess. And so in the application, we're observing documents, and we observe many documents, and the way we record what we observe is we take an n by n by n d times tensor, and in entry I1, I2 through ID, we record how many times that we see a document whose first word was I1, second word was I2, dth word was ID. Okay? And if we observe enough documents that this tensor has to converge to the actual distribution of T. So given this tensor, we would like to recover its decomposition. So what they did, the authors of the paper that I mentioned, they transformed the tensor T into an orthogonally decomposable tensor. They find the orthogonal decomposition, which is which can be done efficiently, as I'll describe later. And then they transform back to the tensor T. And they can do this because they can choose to see the distribution of the first 3 words or the first 4 words. So they have a little bit more information than just this. They can look at this tensor by varying D, and that gives a little bit more information. And they can transform it to an orthogonally decomposable one, decompose it, and then find the parameters. Okay? So in order to explain to you how this works, I need to tell you about eigenvectors of tensors. So given a symmetric tensor T, what is an eigenvector? Well, so for matrices, W is an eigenvector of T if we consider T times W, which is a vector whose ith entry is we sum over J, Tij times Wj, if this vector is parallel to W. Okay? So for when D equals to 3, when we have an n by n by n tensor, W is an eigenvector if Tw squared, which is again a vector whose ith entry is when we sum over J and K of Tijk times Wj times Wk, if this vector is parallel to W. Okay, so this is a generalization of the definition for matrices. And in general, given a symmetric tensor, an eigenvector of T with eigenvalue lambda is a vector W such that if you look at this vector whose ith entry is given by summing over I2 through ID from 1 to n, Wi2 times Wid, if this vector is parallel to W. Okay? And two eigenvector eigenvalue pairs are equivalent if there exists a scalar such that, so the eigenvector scales by T, Tw equals W prime, but now T to the D minus 2 lambda equals lambda prime. So if D was 2 and we were in the case of matrices, we would have, lambda has to equal to lambda prime and Tw is W prime. So we can scale the vector and the eigenvalue stays the same. But for higher order tensors, we need to scale the eigenvalue as well. Okay? And one reason to think about polynomials instead of tensors is that W is an eigenvector of T with eigenvalue lambda if, for the corresponding polynomial, the gradient of f at W equals d lambda W, which is a much easier way of writing it than above. Okay? And moreover, so what does this mean? The eigenvectors are given by all x for which the gradient of f at x and x are parallel, meaning that if we put them in an n by 2 matrix, the 2 by 2 minors of this matrix have to vanish. So these are some equations, and the vanishing of these equations tells us exactly that x is an eigenvector. So this gives us equations for the variety of eigenvectors of a given symmetric tensor. Okay, so here is our example. Let T be e1 to the 3 plus e2 to the 3 plus e3 to the 3, and corresponding polynomial x cubed plus y cubed plus z cubed. Then xyz is an eigenvector of T if and only if the 2 by 2 minors of this matrix vanish. So what is this matrix? We have x squared, y squared, z squared, xyz. So we can remove the factor of 3. So we have these 3 equations that tell us when xyz is an eigenvector. And if we solve the system, keeping in mind that we can't have all x, y, and z equal to 0, then we have exactly 7 solutions. Okay. They're very nice. And if you look at it, the first 3 solutions are actually the elements of the orthogonal decomposition, which we'll later see that happens always. Okay, so what are the eigenvectors of orthogonally decomposable tensors? Well, if T's...
What we are doing now? We are trying to find tensor decomposition of tensor. We are...
So I'm going to tell you what the eigenvectors of an orthogonally decomposable tensor are, and also how to use them to recover the orthogonal decomposition. And also how to find the orthogonal decomposition of an orthogonally decomposable tensor. Okay, so let T be Odeco with this decomposition, some I from 1 to n, lambda I, vi to the tensor power d, where the v1 through vn are orthonormal. Then if we look at the definition of an eigenvector, we see that T times v to k to the d minus 1 equals exactly vk, lambda k vk for each of the vectors v1 through vn in the orthogonal decomposition. So this means that all of these are eigenvectors of T. And so we're going to try to see if there's an easy way of recovering these eigenvectors, which means finding the orthogonal decomposition, and also, are these all of the eigenvectors? Are there any other ones? Because for symmetric matrices, these are all of the eigenvectors. If you know the orthogonal decomposition of a symmetric matrix, basically knowing V lambda and V transpose, so the matrix equals that, then you know all of the eigenvectors. So for tensors, there will be more. Okay, so these vectors in the orthogonal decomposition turn out to be eigenvectors which are a little bit special. Okay, they're called robust eigenvectors. So what does this mean? A unit vector u is a robust eigenvector of a given symmetric tensor if there exists an epsilon such that if we look at a ball of radius epsilon around u, and we pick any point in that ball, and we repeatedly iterate this map. So theta goes to t times theta to the d minus 1, normalized. We always converge back to u. Okay, that's what it means for it to be a robust eigenvector. So note that if theta was any eigenvector, then t theta to the d minus 1 normalized would be equal to theta. Okay, if theta was unit norm. But we also require that if we start in a ball around theta, we go back to it. Okay, so the same 5 authors proved that if T has an orthogonal decomposition like this, then the set of theta which do not converge to some of the elements of the vectors in decomposition under repeated iteration of this map has measure 0. So with probability 1, wherever you start, you're going to converge to one of the vectors v1 through vn. And also the set of robust eigenvectors is exactly equal to these n vectors. So, well, we have to have the lambdas non-zero.
Elina, if the eigenvalue is negative, then it's not robust, I guess? Or?
So, okay, let's say that D is odd. Then, so for the purposes of this paper, to look at n by n by n tensors.
Okay.
So let's say that the eigenvalue is positive for this robust thing. You're right. I think you're right.
Thank you.
You're absolutely right. Okay, so this is a way to. So how do we recover the orthogonal decomposition exactly? So again, this map is called the tensor power method, and sending u to tu to the d minus 1 normalized is the same as sending u to the gradient of the corresponding polynomial at u normalized. So that's also very nice. And what is the algorithm to recover the orthogonal decomposition of T? So you start with some random u in Rn, and then you do the power method and you recover some vector vi. And maybe you have to do a little bit more to make sure that it's robust. Then you find lambda I, which is equal to t times vi to the power d. And then you subtract lambda I times vi to the tensor power d, and then you repeat until t is 0. Okay, and as you pointed out, I guess in this case we require that the lambdas are positive. But for the application, they are actually positive because they come from some probability. Okay. All right, so this is an efficient way of finding it, especially if there's no error, if t is
Is it possible to see let's say, the orthogonal decomposition from the polar ideal? Because essentially, I mean, tensor is orthogonally decomposable, right? If I can apply a change of coordinates and then it becomes x1 to the d plus eta plus xn to the d, right?
Yes. So if you
But this x1 to the d plus xn to the d as a very, very specially polar ideal is should have like a lot of quadrics that kill it, for example, right? If you differentiate with respect to x1 and then with respect to x2.
so you're saying about finding the eigenvectors?
Well, I'm finding the decomposition.
Yeah. So I think it's exactly what I'm going to talk about. So if it's orthogonally decomposable, then I think, let's see, that's exactly. Yeah, I think the next slide will be about this. So first I wanted to say that, okay, so if we have a tensor, or symmetric tensor, then there's a theorem by Sternfos and Cartwright that if it has finitely many eigenvectors, then their number is exactly d minus 1 to the n minus 1 divided by d minus 2. Okay? This is an integer. Okay? And recall that they're given by the 2 by 2 minors of vanishing 2 by 2 minors of this matrix. Okay? So if we're given that T is orthogonally decomposable, can we find all of the can we express all of the eigenvectors? So yes, we can. So let T be a symmetric tensor with corresponding polynomial f equal to this sum I from 1 to n, lambda I times vi dot x to the d. And let V be the orthogonal matrix whose columns are v1, v2 through vn. Okay, then f has exactly the expected number of eigenvectors, and they are given as follows. So what you said, you can imagine that v was the identity. Okay, then we have what we wanted. So what are the eigenvectors? You pick a number k from 1 to n, and you set n minus k of the entries to 0. So in this here, I've set the last n minus k entries to 0, but I can set any any permutation. This to 0, and then the rest of the entries are given by this. You take the lambdas you take to the power minus 1 over d minus 2, and then you pick some d minus second roots of unity. So any d minus second roots of unity. So this will give all of the possible eigenvectors of the tensor. And note that if you pick k equal to 1, so these are all 0 here, then we're picking out the first column of v, which is v1. And if we permute, so if we have just the ith entry non-zero, then we pick out the ith column of v. So this gives us vi. Okay, so this includes all of the robust eigenvectors and more. And here's our simple example as before. Also, basically note that here in this formula, we're taking a linear combinations of the VIs, some weighted linear combinations of the VIs. And in this example, we just have the 3 standard basis vectors and then linear combination, sums of 2 of them and sum of 3 of them. Okay, so things are very nice in this case. All right, and now I want to talk about the set of orthogonally decomposable tensors. So we have a parametric representation where we send a vector lambda and an orthogonal matrix V into the sum lambda I times Vi to the tensor power D. But can we find an implicit representation? Can we find equations that define the variety of orthogonally decomposable tensors? Okay, so the Odeco variety is going to be the Zariski closure of the set of Odeco tensors, now in SD of C to the n. So we take complex.
Closed, like all orthogonally decomposable tensors, is it closed variety or not?
Well, so the way I've written it is it has only real numbers. So.
But over complex number. Define over complex numbers. Is it like closed or not? Zariski closed.
So the way to define it over the complex numbers is by taking Zariski closure. So
maybe the order of the words in the sentence could also be take the Zariski closure in the complex setting of the real orthogonal decomposable tensor. So it's by definition closed.
and so we would like to find equations defining this variety. Okay, and so here's a set of equations that I believe define the variety, but I haven't proven it yet. So this might look a little bit complicated, but if you know the equations defining the Veronese variety, they're basically given by, things like this minus this. So we have some indices I1 through ID minus 1, J1 through JD minus 1, Ks and Ls, such that the union of the I's and the J's equals the union of the Ks and the Ls. And then you take one last index and you sum over it. Okay, so these are basically sums of generators of the Veronese variety. Okay, and so I claim that I conjecture that these are the equations defining the Odeco variety. It is pretty easy to see that they vanish on the set of Odeco tensors. And the reason we take this sum is that, so when we take this sum, basically, if your tensor is orthogonally decomposable, some of these VI's are going to be dotted together, and that's why we have this sum from 1 to n, because of this dot product. And so I've been able to prove it for 2 by 2 by 2 by 2 tensors, but not for larger, so if you can do it, that would be great.
Can I ask you a question?
Yeah.
So, is this Odeco variety the same as is there an open dense in there, which is the image of c to the n times SON c?
Can you repeat?
Is it an orbic closure?
You can complexify it.
I can instead of taking this closure in the complex space, I could first complexify the group, and then ask you the closure. Is that true?
Yeah, sure.
So, and what geometric properties do you know about the what's cut out by these equations? Do you know the dimension?
Yeah, so I think the dimension is the correct dimension, which is n plus 1 choose 2 in this case. But if you have to prove it's prime, and then
Okay.
okay. So now I'm going to talk about non-symmetric orthogonally decomposable tensors. And hopefully after you know about symmetric, then it will be very easy to understand the non-symmetric case. Okay, so, and for the purposes of the talk, I'm going to pick, so T and Rn, tensor Rn, D times. And here I can pick different n's. I can pick n1, n2 through nd, but for the talk, I'll just pick n. Okay, so a decomposition of T is of the form sum I from 1 to R, lambda I, and then we have AI, tensor BI, tensor CI, dot, 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 D letters. Okay, so sum of rank 1 tensors. And an orthogonal decomposition will be, again, so an expression of the form T equals sum I from 1 to n of lambda I, AI, tensor BI, tensor CI, dot, dot, dot. But now we require the AIs to be orthonormal and the BIs to be orthonormal and the CIs to be orthonormal and so on. Okay. Right, and so again, for matrices, if we take a real n by n matrix, we know it has a singular value decomposition, U sigma V transpose, where the UIs are orthonormal and the VIs are also orthonormal, and the sigmas are the singular values of the matrix. Okay. And the other simplest example would be, again, the same as before, but now we think of it as non-symmetric, so sum I from 1 to n, lambda I, and then EI, tensor EI, tensor EI, and so on. So that's orthogonally decomposable. Okay, so instead of eigenvectors, we're going to work with singular vector tuples. So for matrices, so if you have a matrix T, UV is a singular vector tuple of the matrix if there exist two scalars, or two numbers, lambda 1, lambda 2, such that TU, which is a vector whose ith entry is sum over J, Tij, Uj, is parallel to V, and also T transpose V, which is, again, a vector whose jth entry is sum over I, Tij, Vi, if that's parallel to U. Okay? And now for a general tensor, it's a very scary definition. So a singular vector tuple is a D tuple. So we have D vectors, x1 through xd, such that, so if we pick the kth one, and we sum over all indices except for the kth index, and we multiply by the corresponding entry of the vectors. So we have sum over all indices except for the kth one, then xi1 times x ik minus 1 times dot 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 xidd. So basically we're summing over all other entries if this vector is parallel to xk. Okay, so this is exactly analogous to the matrix case, but now it has many indices. But it shouldn't be that much more complicated. Okay, so if these equations hold, then x1.xd is a singular vector tuple of T. And again, so for matrices, if T is a generic matrix, in the sense that the singular values are all different and non-zero, it's positive, then all of the singular vectors are given by the vectors in the singular vector decomposition of the matrix. Okay, and so what about if T is this very nice tensor, so some lambda I, EI, tensor EI, tensor EI. Okay, what are the singular vector tuples of T in this case? Well, if you unravel what the definition meant, it just says that there are so D tuples, x1, x2, xd, that satisfy these equations. Oh, actually, this lambda is different here. So basically, if we multiply all of the, so x1 1 times x1 2 times x1 d, except for the kth one, and we form this vector, it has to be parallel to xk. Okay, and if you write this, so another way to write this is by saying that this matrix that has the kth one vector here and basically the product of the other ones here, this matrix has to have rank 1. Okay? That's the equivalent. That's equivalent to x1, x2, xd being a singular vector tuple of T. Okay. So so we're going to see how to solve this system.
I don't understand because there's no T in this.
So T equals this.
No, but there's no T in your
It's there.
in the matrix that has to be rank 1.
Okay, so we're calling this.
Oh,
It's a special T.
so it's the
It's a very
oh.
special T.
I'm only dealing with
This
that
special
T,
one.
the those lambdas.
And the reason I'm dealing with it is that you can take any other one by multiplying by an orthogonal matrix each of the dimensions.
Okay, so the lambdas are encoding the information of T in that. Sorry.
Is this, I mean, the indices are confusing me, so is
Yes.
this singular vector tuple the same as saying that if I take any n minus 1 versus 1 flattening, and I tensor up these guys, and I get a singular vector pair for that flattening?
I'm not sure.
No,
it's
not.
It's the same as you had before.
Yeah, but
If you contract T
If
with,
you contract, I mean,
so the contraction with all of the x's except the k is a vector in that basis, and the coefficients of that vector is the first column of your bottom matrix, right?
yeah.
Okay, good.
I mean, in the symmetric case, all of these x1 something were the same variable,
Yeah. No.
but now they're different variables.
Yes.
It's like taking the gradient.
Yes, it is like taking the gradient. So there is also a polynomial version of this, but in order not to have way too many indices, I didn't mention it, but yes, it's taking the gradient with respect to this vector. Yes.
It's a critical point.
Okay. So now we're going to solve this system of, so now we're going to find all of the singular vector tuples of this tensor, okay? So first of all, there's a theorem by Friedland and Ottaviani that says that if T is a generic tensor, then it has finitely many singular vector tuples, and they correspond to non-zero singular values, and their number is exactly the coefficient of this monomial in this polynomial. Okay, so there are finitely many of them. However, it turns out that there won't be finitely many of them. for orthogonally decomposable tensors. So this might look scary, but hopefully it's not. So let T be an orthogonally decomposable tensor with decomposition like this. So sum I from 1 to n, lambda I, AI, tensor BI, tensor CI, tensor dot dot dot. And so let A be the orthogonal matrix with columns A1, A2 through AN, and B the orthogonal matrix with columns B1, B2 through Bn, and so on. So if we kind of remove the A, the B, and the C, this tensor is going to be exactly sum lambda I, EI, tensor EI, tensor EI, tensor EI. Okay? And so there are two types of singular vectors. One type is basically exactly the same as what we had in the symmetric case, except it's not symmetric. So we have, k non-zero entries, and then n minus k zeros, and then we have some roots of unity here, and then the coefficients lambda 1 through lambda k to some power. So this is exactly as before. There's finitely many of them. Okay, I can probably tell you how many. But the problem is that now there's this other type, and there are not finitely many of them. So there's a positive dimensional set of eigenvectors here. Okay, so
Can you remind me, what is k? It doesn't show up in the hypotheses, so...
sorry, so k, you can pick any k between 1 and n, which shows how many of these entries here are zeros. And then you can also permute, so not necessarily the last n minus k are 0. Okay, maybe I can write down how many of these there are.
And choose k to
I just didn't keep reading, so now I see it.
Okay.
For each choices of roots of unity, so to sum those, you end up with binomial theorem. This number should be the number from the Friedland-Taviani theorem.
So actually, it is not.
Yeah,
because of the plus and minus.
It's excess intersection.
Sorry.
There's excess intersection, so
Okay.
there's a contribution of each.
So I checked that for 3 by 3 by 3, the Friedland and Ottaviani theorem says 37. This number is 31. But this last, the second type is actually zero-dimensional in this 3 by 3 by 3 case. It's the only case in which it's zero-dimensional, and there's 6 of them. Because you can choose, so this case comes from choosing, so if you take this matrix X, just having entries Xij, you can choose in each row you can choose 2 zero entries, so that no column is all 0. Which in a 3 by 3 by 3, in a 3 by 3 matrix, you can choose basically a non-zero entry in each row. So 2 zeros in each column, in each row, so that no column is 0 is exactly the same as choosing 3 elements like this that don't lie in the same row or column. So there's 6 ways of doing this. Okay, so still correct, I think.
Yeah, well, you'd expect that decomposition just from thinking about excess intersections. You have something for a generic setup, and then when you specialize, there's higher dimensional component, and some of your solutions go to that component, and some of them remain simple and isolated.
Yeah.
Very classical software section theory.
Are the real numbers doing anything in this theorem, or can I just replace it with C everywhere?
So I'm assuming that the lambdas are non-zero.
Well, that happens with complexes too.
True.
It looks like an algebraic result,
Yeah. I don't think so.
especially these numbers you showed there.
Yeah, I think you're right. Okay. And the last thing I wanted to say was the set of equations defining the variety of Odeco nonsymmetric Odeco tensors. Okay, so first of all, the Odeco variety is, again, there's a risky closure. And then we take C to the n tensor power d. And now I conjecture that the equations are the same as before. So you pick, so basically these are the equations defining the Segre variety, but then you pick the, I guess, rth index, and then you sum over, so you put the same s in all of them, and you sum over s. Okay? And since I have some time, I can tell you that one way to think about this is as follows. So, okay, so if T was a matrix, these equations basically say that if you take T times T transpose, this matrix has to be symmetric. This is what the equations say, which it is symmetric, and that's why there are no equations for matrices. All matrices are Odeco. Okay, it's always true. But now if T is a tensor, what we're doing is we're multiplying T by itself over one of its dimensions. Okay, so you choose the rth dimension, and you multiply over T with over this dimension with itself. And I don't know how to denote this. Now this is a tensor in, or so. Okay, now let's say that the dimensions were n1, n2 through nd, because this will be easier to explain. Now this tensor will be a tensor of order 2 times d minus 1, because we multiply over one of the dimensions, but then there's like 2 times the rest of the dimensions. And these equations say that if we take this tensor, it has to be symmetric in each of these components. So basically, it has to lie in S2 of C to the N1, S2 of C to the N2. So it definitely lies in S2 of, the whole product. But the equations say that you can actually switch the coordinates in each. And that's kind of nice, but I still don't know how to prove that these equations are actually the equations defining the orthogonally decomposable tensors. And I think that's all I wanted to say. Thank you.
So in the 3x3x3 case, since you analyze this, rank 3x3x3 tensors have some degree 4 equations that vanish on them. Can you easily see that those equations are in this ideal?
So I think I checked it for the symmetric case, but I don't think I've checked it for the non-symmetric case. So for the symmetric case, you can see that the ideal is prime, and it's clear that. Oh, actually, for 3x3x3, I take it back. I have checked the ideal is prime, and it has the correct dimension. So yes. So it's easy to use Macaulay too, and everything works out.
Do you have also a power method type for computing the Odeco of a non-symmetric tensor?
Yes, so I guess the same people have developed this method, and the way you do it is by alternating each dimension. So you first, so you start with some d tuple, x1, x2 through xd, then you first multiply out, let's say the first d minus 1 dimensions with t, and you normalize. Then you multiply the second, the next, something, you reorder them, d minus 1 dimensions with t, and you normalize, and you do this alternating.
What kind what kind of guarantee do you have that you will recover the whole decomposition?
So I'm not sure, but I think I've heard them speak about this, and I think it's basically the same as the symmetric case. But I'm not 100% sure. I haven't read the actual paper.
Maybe we'll hear some tomorrow.
Maybe we'll hear about it tomorrow. Yeah.
But, I mean, in the symmetric case, should you not, should you not be able to read off the decomposition from the polar ideal? Because you have, essentially, it must come if you look at the quadrics that kill your guy, which is that's to compute them as linear algebra, they must have a lot of common zeros, and these zeros should give you the decomposition. I mean, maybe I'm not via the polarity lemma, because your rank is very small, because the rank is at most n. So again, I'm just thinking that somehow you should be able to get the orthogonal. If it exists, then maybe you can just get it quickly by looking at the polar ideal. But I'm not. Maybe I'm saying.
I haven't thought about it, so maybe.
The polar ideal here is y I y j for
I'm sorry.
I y j different.
Maybe I can make a comment. So if the rank is less than n, then even the catalecticants or the Hankel matrices should detect rank n, and Sylvester's algorithm and its generalization should do exactly what you're saying. And I checked this for several of the examples that this last reference, our algorithm also finds the decomposition for.
Yeah, so the rank here is less than or equal to n, which,
So the catalecticant matrix, the Hankel matrix, will detect that rank and should give the decomposition by essentially what you're saying. Yeah.
So if I had one variety inside of another, and I knew that they had the same dimension, and I wanted to know that they were equal, I might try and cut with a complementary dimensional hyperplane and just count points. And so on the one hand, you have an explicit description of the ideal. Can you compute the degree of the thing that cuts out? That's one question. The other question is, can you, with this slice of this explicit locus you described, can you count points in the intersection of the generic complementary dimension hyperplane?
It's a complementary dimension hyperplane. In planes?
Yes.
Yeah. That'll miss smaller dimension components, right?
Yeah, but I think she knows exactly. We should close something of one component, so.
No, but the ideal she has may have embedded components in smaller dimension.
That's quite the question.
I mean, I haven't tried this, so it seems hard.
No, I mean the one inside can't. Thank your speaker again.